Welcome to this podcast on architectural acoustics, on simulation with Pachyderm Acoustics for Rhinoceros. In this podcast I will focus only on materials, or the application of materials, and specifically absorption coefficients. But just to repeat, we check out first our models for whether it's in meters or not. Put it into meters. And I will then just model something simple here to give us a geometry to work from. Let's see. So let's say we have walls. And we have ceiling, floor layer. Alright, so now we have a geometry with different surfaces that are located in different layers. The reason for this is, as mentioned earlier, is that we in Pachyderm are controlling the application materials through the layers of the model, which is then connected to the geometries of that model. So if you then open now the Pachyderm Acoustics interface, go to the Materials tab, you should then be able to see the new, or the layers represented from the lists of the layers over here. So if you choose a ceiling and floor, we can then start to apply materials to this layer. And as you can see here, there are different layers already included in the Pachyderm as library, as default layers. But you are also able to include new materials that can be applied to these geometries. So the way to do that is to simply write the name of the material here. So let's call that mat1. Doesn't matter what it is just now, it's just for demonstration. And we can save this and it will go in here. So it'll be added to the list to your model. So then you will need to go for each of the absorption, scattering, and transparency, transmission loss, set the coefficients based upon values that you have from literature or from studies in a laboratory or so forth. And the material is then, okay, we can't save it, I have already saved it of course. The material you then apply to that geometry. So let's go to walls instead and say, instead this is glass, apply material, and the predefinition you will already see here, the different coefficients across the different frequencies. And you will need to apply both absorption, scattering, and transparency, or transmission loss, as explained in another earlier podcast. So what we want to focus on in this podcast is actually how you can, when talking about absorption, how you can compute the values of absorption across the different frequencies. And if you look here to call Absorption Designer, we can then press this button and you will be presented to a quite extensive and large interface here, which basically is a materials designer in relationship to the properties of the material in relationship to absorption. So if you quickly look here, we have here the absorption coefficient that will be computed across the different frequencies. But we also have here an empty space, which will include a polar plot when we have built up the material and start to simulate the absorption coefficients or the absorption properties of the material buildup. We here see the impedance of the material, the opposition in the material. And we have also then here the setup for the size of the specimen that we are simulating and the method that is applied to this. So we are interested in absorption, and the way to build the material that you are looking to create for absorption properties or absorption coefficient calculation, there is here under sample type a list of different materials. So you have here airspace, different porous absorbers, or different methods of calculating porous absorbers, and then perforated solid plate, perforated and slotted plates over here. What you should take notice is under the perforated and slotted plate is that you should use model solution, the model solution types here, whereas the other ones they are still in development. So modal solution are the ones to go with for the time being. But let's just start to apply an air gap on airspace in your construction. Let's maintain the settings here, and then you can change the material depth of the structure according to what kind of setup you have. And then you simply add the layer, and you'll see that the layer is added up here in this space. We do not have any absorption because we only have added air. So the same goes for over here. So let's then include a porous absorber. And here you get a little bit more possibility to specify that material properties. So the airflow resistivity and the porosity of materials, you can include the properties of here. Now I'll just maintain the same because in any case it will be specific for your specific projects. Add the layer, and it will compute the absorption coefficient based upon these two properties, or these two materials combined. So immediately we start to see a plot here. And what we can see is that it's calculated for both the normal incidence, so the calculation taken into consideration if the sound energy arrives as a normal vector to the surface, but it also includes a calculation if there's a random incidence of the sound energy. And as we see here, we have porous absorber only, which means we have absorption in the higher frequency fields. One thing to notice is also you can change the angle of incidence here. What we see over here is very interesting in the sense that we do not only see the calculation of the normal, but we also see it in relationship to angles of incidence, where the absorption coefficient will then change, as described in an earlier podcast also. So here we already have a material or specification of the absorption coefficient properties to a specific design. So if you then choose, let's say, perforated plate, modal solution, again we just maintain the depth. And here you have the hole diameter, the size of the hole, and the hole pitch, the distance between the holes. Again, we leave them by the defaults. We apply it, nothing has happened because it's still computing the absorption coefficient based upon this new construction. We'll give it a minute, see if something happens. Right, so here we got the change of the absorption coefficient after having included the plate in front of the porous material, and we will see a change both on the curve here, but also on the polar plot. So one way to go about this in terms of absorption coefficient is that we could now simply take the values that we can see in the graph and then apply them over here to our material by changing the different values here and save that as material. But what is very smart in this sense, and why I think it's the reason why Arthur has called it a smart material, is that we can also include the richness of the polar plot, so that the absorption coefficient has its dependencies of the angle of the incidence included in the calculation of absorption coefficient when later simulating. So what you'll do here now is to simply create smart material, and you will see that information of the polar plot in respect to incidence of absorption is now included in this material. So in this sense, you start in terms of absorption coefficient to have a very high specificity of the properties and the behavior of that properties in relationship to material definition, and later, of course, how this influences the performance of simulation and the performance of the space. So in summary to this podcast, this very focused podcast on materials and the definition of absorption coefficient in Pachyderm. Materials are defined through the geometries and through the layers. They're included into the interface. And here you can choose predefined materials. You can define it yourself through simply going through the different sliders or put in specific numbers based upon references. Or you can compute the absorption coefficients and the specificity in relationship to incidence through the interface in Pachyderm. Thank you for watching this podcast.